it. Great. So having said that, our first talk this morning will be given by Haggard. He is not only a phenomenal researcher, but also a great instructor. So we asked him for the daunting task to review all of loop quantum gravity and spin foams. And luckily, he was up for it. So I'm very excited to learn more from you, Hal. The floor is all yours.
Good morning. Thank you for being here. I want to add my thanks to everyone else, to the organizers. It's been an incredibly tightly run and wonderful conference so far. As Beatrice says, I have 3 fields to overview. They asked me to do loop quantum gravity, spin foams, and my own research. So I'm going to go at quite a clip. If I'm going too fast, wave your hands and I'll try to slow down a little. So just to give you the barest overview of what I'll be talking about, loop quantum gravity is the Hamiltonian approach to quantum gravity, where we make a space-time split and we consider the theory from that perspective. In particular, it's a gauge-theoretic approach to quantum gravity, and that's going to be where I'll start out, and I think it's a compelling aspect of the theory. On the other hand, spin foam models are a discrete geometry path integral. So it uses the same sort of algebraic structures that underlie loop quantum gravity, but it's a path integral approach and is where we're attacking the dynamics of the theory. So I'll give you the talk in 3 parts. I will overview loop gravity first, and then I'll do the short interlude where I'll introduce you to some of my own research. And then from there, we'll go on to the discrete geometry path integrals. The 3 parts are mixed intentionally, and in particular, my introduction to the spin foam approach will be non-standard. So there are excellent reviews of the so-called EPRL spin foam and FK spin foam. You can check out Alejandro Perez's review, but I'm going to give you an introduction to some of the approaches that have been developed in recent years, and in particular try to emphasize what I think they've taught us about spin foams. All right, as I already said, loop quantum gravity is a canonical approach, and so we make a space-time split. But the symplectic structure of the theory in the standard metric variables doesn't cast the connection as one of the canonical variables. And if we'd like to see GR as a gauge theory, it's very nice to have the connection at the fore as one of our variables. So in the ADM formalism, the oldest approach to canonical quantum gravity, you split the space-time metric into a spatial metric and a lapse and shift piece. And in particular, the canonical analysis leads you to consider the extrinsic curvature. So here's our spatial slice sigma. And we think of the extrinsic curvature as being how this slice is embedded in the space-time. And that leads us to a canonical momentum, which is actually given by essentially that extrinsic curvature. In the approach that we'll be taking, where we try to center the connection at the fore, we're going to shift to a different set of variables. And the first part of that shift is to reorganize which part of the metric we think of and to introduce this densitized triad. So it's just like a tetrahedra variable that you may have seen in classical GR, but it's a triad, a frame field that lives on the spatial slice, and it's been densitized by the determinant of the spatial metric. You can recover the metric, of course, from the triad. And in particular, the variable that we'll be focusing on a lot, because it's a very useful way of framing this triad, is in terms of a 2 form. So we call this the electric flux 2 form. Then we need the connection variable that's going to be the other half of the canonical pair that we think about. And to do this, you take the spin connection. So we're thinking of a Lorentz bundle that's living over the same space-time. We take the spin connection of that Lorentz bundle and we break it into its boost and rotational parts. And from the rotational part, we can build a connection variable that has the same index structure. Just using the Lorentz bundle's internal Levi-Civita symbol, we can take this spin connection spatial piece and turn it into a connection. In particular, if we require that our triad variable is metric compatible and torsionless, then the same sort of thing that you're used to from tetrahedral variables comes through, and you can cast this connection as being a function of the triad. All right, so this choice of variables is what makes loop quantum gravity into a gauge theory. In particular, if we take, again, another contraction of the extrinsic curvature with our triad variable, we can build this index structure for the extrinsic curvature. And we take our ADM kinetic term, and you can see how it is re-expressed in terms of these curvature and triad variables. And in particular, you can pick out the kinetic piece in that variable. And what we see is that the densitized triad and the extrinsic curvature are the canonically conjugate pair. So this is our PQ dot in the formulation that we're headed for. So this allows us to set up schematically this Poisson structure. We had that Q and pi were conjugate, and by this change, this canonical change of variables, we have arrived at K and E being canonically conjugate. Unfortunately, K is still not a connection, but we take advantage of something that you know well from your GR courses, that the difference of two connections is always a tensor. So we can add any tensorial structure to our connection, and it's still a connection. So this is where the Ashtekar connection comes from. You take the spatial part of the spin connection that we already were discussing, and you add I times the extrinsic curvature. And this is your basic connection variable in this approach to gravity. This is a beautiful idea. It mixes the two pieces, you see. The canonical conjugacy is going to come from the K piece, while the fact that it's a gauge connection is coming from this spin connection that we were taking advantage of. So this is what gives the Ashtekar variables this canonical structure in this approach to GR. This is a beautiful gauge theory in my mind. This is the foundation, the root of loop gravity, and what I think is one of its most stunning structures is that the action becomes a completely constrained system. So we have the kinetic term that we just described, and we have three Lagrange multipliers that impose three constraints. These are the completely constrained part of the theory. Those three constraints are the Gauss constraint. This is the gauge theoretic piece that you would be used to. This is the SU2 gauge part. We have a spatial diffeo piece, the vectorial constraint, which is built out of the field curvature of the connection we've introduced. And it's just the contraction of that. And we have the scalar constraint, which is, again, a polynomial in the E's, quadratic at most quadratic in the E's, and quadratic in the A's. So this is not only reformulated GR as a gauge theory, but it's also cast it as completely polynomial constraints, and the action has become polynomial. So this is a beautiful approach to GR. It's completely equivalent to GR as a classical theory. You know there's a catch coming because it's quantum gravity. And so the catch is that this I that you couldn't have missed in the definition of the Ashtekar variables. So in terms of I, a slightly further analysis than I've given you here shows that the boost part of the spin connection is actually related to the extrinsic curvature. You can do this by analyzing what's called the Holst action. And there's this nice structure that we're taking advantage of, that the Lorentz algebra, SL2C, can be split into SU2C plus SU2C. These are the self-dual and anti-self-dual sectors of the theory. So this choice of variables that we've just made is taking advantage of that, and we're nicely introducing a connection that is encoding in its real part the parallel transport of the spatial piece of the field, and in its imaginary part the parallel transport of the, say, RT plane. So this is a gorgeous way of thinking about this connection. But to make sense of it in a quantum theory, we would need to know how to extract those two pieces, to extract as operators what the real part and imaginary part of this connection are. And so far, that's remained a challenge. Despite being a challenge, there's a beautiful recent paper by Stefan Alexander, Herzog, and Laurent Friedel that one of the things they asked me to do was advertise places where, as students, you might think about looking. And they've introduced an inner product that's based on the old work of Bargmann. And it's a complex inner product that allows you to do some of this pulling out of the real and imaginary pieces. It's not a complete story, but it's got a really interesting avenue. And this is one place that, as a young person, you have all these experts in quantum gravity who've tried the reality constraints much of their career. It's your chance to see why that doesn't work, ask them about it, see whether this is an avenue of progress. I think this is a good time to think about this question again. Nonetheless, what people have done instead, since they've struggled with these reality conditions, is to modify this Ashtekar approach and to introduce real connection variables. So it's the same spatial piece of the spin connection we talked about in extrinsic curvature, but instead of putting an I here, we put a gamma. And gamma is a real parameter. It's a new parameter in the theory. It's often called the Barbero-Mirzi parameter because these two researchers introduced this way of thinking about the connection. And I'll mention what its physical import is later in the talk. But for now, I just want to give you a brief overview of a kind of tension between different variables. So we've seen already that the Ashtekar variables give us nice Poisson commuting connection. And they actually behave well. I didn't say this before, but they behave well with the constraint algebra. In particular, that scalar Hamiltonian constraint that we saw, when you see how it acts on this connection, you see that at least on shell, it acts as a diffeomorphism. So this is a beautiful aspect of that Ashtekar connection. Unfortunately, at the quantum level, the reality constraints have been hard to impose. So this Ashtekar-Barbero connection has a different trade-off. With the Ashtekar-Barbero connection, you have a real variable. It's still Poisson commuting, so you retain that advantage of the formalism. But it doesn't have a nice algebra with the Hamiltonian constraint. So I'm calling that algebraic aspect space-time covariance here. It's much harder. You can see why this is happening, right? We're no longer cleanly separating the spatial part of the parallel transport and the boost part of the parallel transport. We're mixing these two things. And I, for one, don't have a good geometrical way of understanding what that mixing is doing. So that's the disadvantage of this real variable. Nonetheless, this is the path that is most taken in loop gravity. Just to finish out this classification of connection variables, there's a nice paper from the early 2000s. Alexandrov worked out a third possibility. He studied the most general connection you could have in this context and showed that you can do the third option. That is, you can have a real variable. It's closely related to these Ashtekar-Barbero variables that does have a good algebra with the Hamiltonian constraint. Unfortunately, this time it's no longer Poisson commuting. So if you want to try and construct a functional representation of wave functions on the connection, this becomes a difficult path to go down. So we don't know of any path that has all three of these properties at the moment. And as I was encouraging you a moment ago, I'm very curious, and I think one of the most beautiful aspects of loop gravity is this Ashtekar variable. I'm curious if we can push this further with the knowledge that we've gained in recent years. All right, so we've cast general relativity as a gauge theory. We're interested in quantizing it, and so it's natural to look to gauge theories, and lattice gauge theories I'll make a lot of comparisons with for what kinds of observables we would look to. So in an abelian gauge theory, you have the so-called electric and magnetic fields. They're nice local observables, and you could work with them. In the non-abelian theory, the field strength is no longer gauge invariant. And this isn't a great option for looking for gauge invariant observables. You could also look at a sort of transverse traceless gauge and think about that. This is still possible. In fact, this is related to a lot of the work that's been happening on corner symmetries, BMS algebras, and things like that at infinity. But if the final option, the one I'll pursue for now, is that you can look at holonomies around closed loops. This works both in the abelian case, where the gauge transformation is killed by such loops. And as long as you take traces, so-called Wilson loops, of these holonomy observables in the non-abelian case, this is again a good observable. So why aren't these used more in, say, lattice QCD? Well, in lattice QCD they are used, but in continuum approaches to Yang-Mills theory, well, the reason is that these Wilson loops have the difficulty that they distinguish loops that are even slightly different from one another. So another really elegant aspect of loop quantum gravity is to use the huge gauge group that we have in the theory to address this and to make Wilson loops into good observables. So the way that we do this is that we have not just the gauge, the SU2 gauge theory that I was introducing, but we have the huge diffeomorphism symmetry of the manifold. Here we're implementing it as the vectorial constraint and the Hamiltonian constraint. But nonetheless, we can use the spatial piece of that diffeosymmetry to identify these two loops. So in loop quantum gravity, we're leveraging these two things against each other. Usually Wilson loops are our difficult approach, but here, because of the diffeosymmetry, we can recover them as nice observables. In fact, the spin networks that you've heard a lot about already at the conference and that we work with so much provide a basis of inequivalent loops. So even if we have diffeos identifying two loops like this, graphs with vertices, well, they can't be diffeomorphically transformed into each other. This depends a little bit on the technicalities of what kind of diffeosymmetries you're thinking about, but graphs and knots are not equivalent loops. So spin networks provide a basis for these inequivalent loops and give us good things to calculate Wilson observables on. So the idea then of loop gravity, the quantization that we'll be thinking about, is to introduce a Hilbert space based on these group variables, which are the holonomies. So this would be the SU2 group, and using the Haar measure. In particular, we'll consider graph embedded in space-time. On that graph, we will have L links, which I'll label by indices little l, and n nodes labeled by little n. And you can have holonomies along every link. And so just by tensoring this Hilbert space, we get a Hilbert space for the graph. Finally, we need to take the gauge invariance at the nodes of the graph into account. And so we divide at the nodes by SU2. And we have a good Hilbert space for graphs. To define an inner product on this Hilbert space, we leverage another tool from lattice gauge theory, which is a so-called cylindrical consistency. So I'd like to be able to take the inner product of a state on one graph with the inner product of a state on another graph. But to be able to do that, I would need to be able to see both of these as being in the same Hilbert space. And so the idea is to embed smaller graphs in larger graphs where I just color the link that is additional with a 0 representation. Then it doesn't contribute to my inner product, and I can think of both gamma and gamma prime as subgraphs of this larger graph and take the inner product there. So this gives us an inner product. And as we consider the refinement limit of more and more finely worked out larger and larger graphs, we approach a continuum theory. There are important differences with lattice gauge theory, as well as all these analogies that I've been telling you. So in a lattice gauge theory, you would have a lattice spacing, and that lattice spacing would mean something physical. It would be the physical distance between, say, the atoms of your theory. But in this approach, of course, we don't want any background metrical structure. The metrical structure is what we're computing on the links of the graph. And so the refinement limit is actually the limit where we're capturing more and more degrees of freedom. So this is a subtle and delicate aspect of the theory that's much under study. All right. So the summary of this first part of the talk then is that we have a well-defined construction of a kinematical Hilbert space This is the Hilbert space on graphs that I just described for you, which consists of cylindrical functions, so functionals of the connection variable, which we compute holonomies along the graph of, and we develop a wave function of those holonomies. So the physical content of these wave functions is that they're probing the space-time curvature around closed loops of our graph. Through this discussion, I've abandoned the metrical degrees of freedom. They've become hidden. And so in the next part of the talk, I'll try to overview briefly where they are. I'm going to do this in a very simplified context. But the idea is to go back and look at the Gauss constraint. I left it behind because you know well how to study Gauss constraints and how to solve them. We can think, for example, of integrating the electric two-form that we introduced above. The only thing that's new here is a basis for the SU2 algebra. Integrating it over a closed surface, and of course this gives a notion of an oriented area for this surface. Because the surface is closed, that orientation closes up, and we have 0. So this is a way of thinking about solving this Gauss constraint. Even though this is something you know well and is sort of trivial, there's also a beautiful aspect of this that, because the theory is non-abelian, you may not have noticed before. So this is picking out an oriented area, but oriented how? And here the idea is that the orientation is a local orientation. This is much like how the wonderful Jim Hartle, these figures are from Jim Hartle's undergraduate text. Unfortunately, he's just passed away. He gives a beautiful description of how we measure energy of particles, right? We have a local laboratory. We set up a local inertial frame in that laboratory. And what we mean by the energy of the particle is the particle as measured in that orthonormal frame. So the same idea is what's at work here. The orientation of this area element that I was just showing you is that I set up a little region of space-time in my laboratory, and I measure the areas in that space-time region. Of course, if I want to be doing, this laboratory is supposed to be a weak field laboratory. So you're either considering very small regions of space-time or very weak fields, whichever limit you like to think of. So a particularly nice and simple example of this is to imagine that I just have a simple polyhedral region in my local laboratory. And I'm going to measure the area fluxes in that local frame. And the closure constraint just becomes the simple addition of the vectors associated with each of the facets of that polyhedral region. So Gauss closure becomes closure of my geometry here. Here it's just a Euclidean flat geometry. And wonderfully, this is exactly the characterization of polyhedra that Hermann Minkowski gave at the close of the 20th century. So he showed that convex polyhedra are in one-to-one correspondence with vectors that add up to 0, where each vector is equal to, each vector has direction perpendicular to the face of the polyhedron and area equal to the magnitude of this vector. So this is a one-to-one correspondence between polyhedra and their description in a local inertial frame. A very small piece of geometry that is kind of trivial, but that we're going to use briefly. You probably know well that the volume of a tetrahedron can be written as the triple product of its edge length vectors. There's a factor of 1/6. But something that you may not have ever encountered is that you can do the same thing with the area vectors, actually. Simply write any area as the cross product of two edges and work out the triple product of the areas, and you'll find that it's precisely the volume squared up to a numerical factor. All right. So beautifully, this closure constraint that we're seeing plays a dual role in the theory. On the one hand, we're saying it determines the local geometry. It's the metrical geometry of, say, a convex polyhedron, but you can use any closed two-surface. But it also is the generator of the gauge transformation. It's the Gauss constraint, right? And we know that's what's happening here because the internal index is also an SU2 algebra index. That was the whole point of it. This was our gauge theory. So this closure constraint generates rotations, and this has a very clear interpretation. The metrical geometry of the tetrahedron doesn't care about how the tetrahedron's oriented in space. That's pure gauge. All we care about is the relationship between these flux vectors, and that relationship gives us the shape, the metrical shape of this region. This actually, stunningly, has to do with a beautiful gauge system description of a cat. I don't know if you've ever heard of this, but if you hold a cat upside down, yes, people do this, you can see the hands at the top there, and you let it go, the cat will turn over. But if the experiment's done carefully, you release the cat with zero angular momentum, right? And that's what our Gauss constraint is saying, zero total SU2 algebra flux. And wonderfully, even though you've released the cat with zero angular momentum, it turns over. How does it manage to do that? It has internal degrees of freedom. It can change its shape. So even though its total angular momentum is zero, each of its pieces can have non-zero angular momentum, and the cat can be described by a gauge theory, which allows it to change orientation, land on its feet, with zero angular momentum. It's a remarkable thing. But that's exactly the metrical geometry we're describing. Tetrahedron is described by its four face areas. They add up to zero. The four face area vectors add up to zero. So the total angular momentum of our shape is zero. But there's enough internal degrees of freedom. That is, we've only fixed 4 of the face areas, not 6 edge lengths, right? Even if we fix the volume, we've only fixed 5 of 6 quantities. So the tetrahedron can change shape without changing area or volume. So this is the gauge system that we're describing here. This is a video I was going to try and play for you, but after yesterday's experience, they said no more videos. So I'll try and load this on my website by tomorrow. It just shows 2 perspectives on this tetrahedron. The phase space turns out to be a sphere. As it evolves around this curve, it changes shape without changing areas or volume. So you can actually see this as a classical dynamical system. Okay. It's time to do some quantization. We haven't done enough quantization of this metrical side of things. But the observation that these are isomorphic as algebraic systems with angular momentum gives us a beautiful strategy for quantization here. We can just leverage your undergraduate quantum mechanics and study the system as irrep spaces. We can take Hilbert spaces, which are carrier spaces for SU2 irreps, and the action of these angular momentum vectors is precisely the action that you're used to. So the electric flux operator acts on a Jm basis as the square root of j times j plus 1 on that basis. The main impact here is that the unit structure of the gravitational field gives us an area outside instead of the h bar that you're used to from angular momentum theory. Well, that area is proportional to h bar, so it's the same in that sense, but it's the g. It carries a g as well. And so this is describing a Planck area. So we get a discrete spectrum for geometry out of this description of the theory. Here you see also the Barbero-Mirzi parameter reappearing in the theory, and its appearance now gives us a physical interpretation. Gamma is we've seen that now that it's got a spectral spacing like angular momenta, and gamma is determining how big the physical space between spectral steps is. So you can think of gamma as a sort of area gap, as fixing the area spacing of this geometrical structure. Of course, it would be wonderful if we could just directly probe whether space-time had spectral discreteness. Unfortunately, you probably know that the Planck area is of order 10 to the minus 70 meters squared. And so you and I are closer to the size of the entire observable universe than we are to the size of these spectral grains. So hard empirical problem there. All right. These Jm basis carries, of course, the magnetic index as well. That magnetic index betrays the fact that if we are thinking of one of these facets, it has an orientation dependence in space. But we knew that we wanted to describe the gauge invariant geometry of this grain. So we want to combine each of the facets in such a way that we have a rotational invariant. And the key to doing this is to look for tensors within this tensor product of Hilbert spaces. the 4 facets, look for a tensor in here that can contract with these JM states and give you a rotational invariant state. So that tensor is known as an intertwiner. It's the one aspect of angular momentum theory you may not have encountered here, although if you studied Clebsch-Gordon coefficients, it's roughly the same idea as the Clebsch-Gordon coefficients. So we contract the JM states with this invariant tensor, and as such, we get the gauge invariant state. This is what I was doing earlier, but I was kind of glossing over it. I said I was modding out by overall rotations at each of the nodes, and this is how we do it. We choose an intertwiner, not just a spin label on the edges of the graph, but an intertwiner at each node. Not only that, but you can choose nice, physically meaningful intertwiner states. So we've been seeing already that the classical geometry of a tetrahedron would suggest that you could introduce a volume operator for each of these grains given by a triple product, and indeed you can make this rigorous. So this has been done very carefully in the canonical literature, where they look at regularization of this operator and carefully check that indeed this gives a sensible operator. But I'd like to point out that even in the 60s and 70s, Lévy-Leblond and Chakrabarty and company were already thinking about this in the context of angular momentum theory. So one of my jobs that they gave me today was to try and make interconnections. And beautifully, J.J. Carrasco was talking about these huge number of diagrams that we get from double copy theories. Beautifully here, the spin networks are actually doing that same kind of organization of diagrams for us in the theory. The spin networks are taking all these graphs and organizing them into nice pieces where we can pick out physical basis states like this with the volume and the areas labeling the intertwiner and the facets. All right, I am gearing up for the last part of the talk. And I'm going to make a change of notation here. I'm sorry for this, but I struggle to keep consistent notation throughout the whole thing, so I'm just going to do it explicitly so you see me do it. Up to now, I've been putting emphasis on the Ashtekar electric field, the fluxes, and I was careful not, to call them electric fields and not something related to area because we also had the Ashtekar connection in the game. But at this point, it's going to be convenient for me to switch notation. I'm not going to be using the Ashtekar connection so much in what follows, and so I'll shift from calling these E vectors to calling them A vectors to more directly give you the intuition that their magnitudes are equal to areas. At the same time, I'm also going to give you labels for the different pieces of our tetrahedral grains. The edges I'll call E, I'll label with indices E, the triangles with indices t, and the tetrahedra with indices tau. All right. That's all set up for the spin foam approach we're about to take. But before I go there, I was asked to also tell you about some of the things I've been doing in my own research. And this connects nicely with Bianca's overview talk that she gave on the first day. I want to emphasize that this setup is extremely well positioned to deal with both Euclidean and Lorentzian geometries. And here's one way of formulating that. You can check that the Minkowski theorem works just as well whether you're working in a SU2, SO3 is isomorphic to SU2 as an algebra, of course. So whether you're working in the Euclidean context or in the SO2-1 context, in both cases, closure describes the algebraic structure of a closed geometrical polyhedron. In the latter case, you may not have been used to thinking about a tetrahedron. We mean a space-time tetrahedron here. So one way to think about this is you and two of your friends are playing soccer in a big parking lot, and the soccer ball happens to be between you somehow, and three of you run at the soccer ball at the same time, and you end up meeting at the soccer ball. That would be a tetrahedron in space-time, right? You're separated spatially by a triangle. As time evolves, you come together to a point, so that would be a Lorentzian tetrahedron. That tetrahedron has the same space-time description as the Euclidean tetrahedron I was just explaining for you. Not only that, but beautifully, you can cast the volume that we were just studying, this triple product, as a determinant. And if you like, you could square that. And the determinant squared, well, that immediately leads you to a so-called Gram matrix, a matrix of dot products between these vectors. And the leverage that you gain by doing that is that this dot product, I can interpret it as being in a Euclidean R3, and it's just the standard Euclidean tetrahedra you're used to. But if you like, I can also interpret it in a Lorentzian R21, in a Minkowski space. And when you interpret it in that latter way, you find that, well, taking determinants, I would have to insert the determinant of the Minkowski metric in the middle here. That would just give me a minus sign. And the sign of v to the fourth, oddly, v to the fourth, this is not something we're used to, the sign distinguishes whether you're talking about a Euclidean tetrahedron or a Lorentzian one. So this is actually beginning to go into this interesting world that's been opening up in the community in the last year or two of working with an area metric. This Gram matrix is the simplest possible example I know of a so-called area metric. It's where we're studying the geometry of these grains via the areas instead of via the lengths. This is very much in harmony with the symplectic structure of general relativity. It's why we're doing this, why people are pushing in this direction. So something wonderful that I've been working on is that using these area variables, you can cast this volume. You just take that determinant we were looking at, and you can cast this volume as a cubic in the couplings A12, A23, and A13. If you work in those variables, you'll quickly see that actually the sum of these three couplings is precisely the sum of the four area squareds. This is a quick calculation. But if I combine these two algebraic identities, I have a cubic curve in the plane. And remarkably, cubic curves in the plane are one of the most mathematically well-studied objects in the whole of geometry. These are known as elliptic curves. So what we've just shown is that there's a correspondence between tetrahedra and elliptic curves. And this gives us a new tool for the field that I'm really quite excited about, because elliptic curves are one of the places in which Diophantine analysis of geometries that have integer solutions, are best worked out. So suddenly the quantization conditions, which make these angular momenta into integers or rational numbers, those quantization conditions are suddenly very harmonious with the geometry of elliptic curves. And what's particularly stunning to me here is that you couldn't have done this unless you had appreciated that both Euclidean and Lorentzian geometries contribute to this. So the correspondence with elliptic curves wouldn't be complete unless you allowed for the Lorentzian signature. So we have an avenue now for kind of classifying all quantum tetrahedra in space and space-time via their elliptic curves. If you haven't ever studied elliptic curves, I understand. It was an area I avoided, but you should know that this was at the heart of the proof of Fermat's last theorem. So that's a beautiful example of the way in which they interplay with Diophantine problems. Not only that, but something that's really striking about elliptic curves is they have a geometrical construction of a so-called group law. It's an abelian group law, so people often represent it as addition. But the idea is very simple. You pick a point on the elliptic curve. You can take the tangent to the curve at that point. Because it's a cubic curve, it will intersect at a unique second point. And by taking the vertical through that point, you construct what's called the addition law on the cubic curve. This is the doubling. Because I took a tangent, it's giving me the doubled point 2p. But you could also take something that goes through the curve, not the tangent. If you took 2 points on the curve, you took the line through the two, you'd get a unique point. You reflect, and you get the sum of those 2 points. So this defines a mathematically precise group law on elliptic curves. And now we have a remarkable interpretation of this in quantum gravity, which is that you can add tetrahedra. So there's a group law, a well-defined mathematical group law. And in particular, what I find interesting in this case is you can add 2 Euclidean tetrahedra, and you end up getting a Lorentzian tetrahedron. So I don't know how to interpret this in the quantum theory yet. This is work in progress. But I'm just trying to illustrate the ways in which the correspondence with an elliptic curve is going to be an interesting tool for thinking about quantum geometries. All right. So the last part of the talk, I'll try to give you an overview of the path integral spin foam approach. I'm going to take, as I said, a non-standard path to this. I'm going to introduce you to what we call effective spin foams. One of the reasons I'm doing this is that they highlight a feature of spin foams that I don't think is always highlighted, and I think it's a good thing to expose people to and to get your thoughts on. The approach I'm going to take is going to go through what's called Regic calculus. Regic calculus was invented in the 50s and 60s by Tullio Reggi. And the idea is to describe curved spaces by giving piecewise linear approximations to them. So if you think of a two-dimensional surface, I chose Mount Rainier because I went to college. I went to Reed College, and Mount Rainier was out our back window. So this is a beautiful landscape. And Scott Bailey made this wonderful picture. I don't think he had Regic calculus in mind, but this beautiful painting of Mount Rainier you can see here is in a Regic formulation. So the idea of Regic calculus is you take these piecewise linear regions, and instead of completing this into a flat plate, you remove one of the triangles and identify the remaining edges, and this concentrates curvature at the pink dot. It's easy to get confused here between the intrinsic and the extrinsic curvature. The embedding means nothing in this picture. I'm not talking about the curvature between these two triangles. I'm talking about the intrinsic curvature. If an ant parallel transported a vector as it went around this point, it would find a concentrated curvature at this tip. But you can do this at every dimension, and there's a rhyme with what we saw in the canonical theory, which is that you have a choice to make. You can work with edge length variables, that is the standard metrical variables. But if you do that, the canonically conjugate quantity is a disgusting mixture of angles and very hard to parse. The alternative is to work with the area of triangles, with the area variables that I was describing for you. And if you work with those area variables, well, then the curvature angle, the codimension 2 surface is a triangle, and the curvature variable is just the angle that you get on parallel transport around that triangle. So this is a beautiful harmony with loop gravity. It's much nicer to work with the area variables in Regic calculus. So I'll do what we call area Regic calculus. And in area Regic calculus, there's a problem right at the outset. And it's a problem that actually confused our community for quite some time. Luckily, I think it's been clarified a lot in recent years. So in the standard length Regic calculus, where you treat the edge lengths as your variables, you get good equations of motion. That is, as we refine the graph that we're studying, we recover the Einstein equations. But if you work in area variables, the Regic action is actually quite simple. It's simply the product of your areas with the deficit angle at the bone. The deficit angle is just defined as 2 pi minus the dihedral angles as you go around that bone. So it's really measuring that deficit that we were seeing in the first picture. And we can cast that deficit angle as functions of the areas. So we're just thinking of these dihedral angles as functions of the areas. If you aren't sure how to do that, you can just go through the length variables. So you invert the length variables for the area variables and recover the dihedral angles that way. But the trouble that you run into is that when you take the variation of this discrete action, well, you get the curvature, and then you actually immediately have a classical differential geometric identity called the Schlafly identity that kills this second variation. That is, for all geometries built this way, this term is 0. And so your equation of motion becomes that your curvature is 0. So this is a disturbing aspect of area Regic calculus that caused people a lot of concern. They were worried that spin foam theories that are built on area variables might just always be flat. But there's a way out of this. And the way out of this is to think carefully about how we're gluing these 4 simplices. We want to build up a triangulation of a 4-manifold, and the way you glue 2 4 simplices is you pick a tetrahedron. Say the tetrahedron picked out by these 4 orange dots, and we're going to glue it to a second tetrahedron. In a length Regic calculus, you're gluing 6 edges, and they just geometrically match. Everything is fixed, and you can't go wrong. But if you're using area variables, those two tetrahedra only have 4 area variables. And it's clear that when we glue, we're not fixing the geometry of the two tetrahedra. Just getting the areas to match isn't fixing their Euclidean geometry. And so this does somehow have more flexibility than you would get from a length Regic calculus. And so the strategy is to introduce more variables to make sure that the gluing is somehow good. So what we do is we work with that areagram matrix I introduced you to before, that we simply include 2 more variables in the theory, the dot products of 2 of these normal vectors. And now we have 2 of the dihedral angles. It turns out that you have to be careful. They have to be 2 edges that are non-opposite in the tetrahedra. But if you include them as variables, you can impose a nice constraint on the theory that makes these 4 simplices glue well. Nonetheless, there's a catch, as there always is. And the catch is that if you look at the Poisson structure of that tetrahedral gauge theory I was telling you about, you'll find that those 2 dot products that I just introduced you to, they don't Poisson commute. Their Poisson bracket is proportional to the volume, where the plus or minus sign here has to do with the Euclidean or Lorentzian geometry. So this set of constraints is second class. And you probably know that if you can't impose a second-class constraint strongly. And so you have to be more careful about how you impose this. You have to impose these constraints in a weak manner. So this is at the heart of what I wanted to tell you about spin foams, and that I think is something that the community is appreciating more and more right now, which is that whether you make it implicit or explicit, always behind your spin foam theory is some gluing rule. Some way in which you're matching tetrahedra, and often that way has subtleties embedded within it because of this non-Poisson commuting aspect. All right, so just to tell you finally how we define the spin foam, again, here's the deficit angle formula we were looking at before. You plug it in. It's easy to include boundary triangulations. I just include an index here that is either 1 or 2 if the triangle is in the bulk or on the boundary. And then you can nicely split up the area Regic calculus action into a piece that's a sum over triangle and a piece that's a sum over simplices. And the 2 pieces are defined down here. And here's where the quantum ingredient comes in. So there's 2 things. The emphasis I was just giving you, here's the Regic calculus action, but we are going to add in a piece, which is our gluing constraints. So that's where in the action we've encoded the gluing constraints. And then the second thing is that we're going to add in the quantum piece now, which is to use these area spectra that we just saw earlier in the talk. So this is what's going to turn this into a partition function path integral model. And we have to be careful here. Bianca used this analogy early in our work together, and I fell in love with it. We have to navigate very carefully between 2 dangers. If we impose the constraints too strongly, we're going to have an issue of, so this spectrum, of course, doesn't allow every area. You only have the spectral spacing that you have. And because of that, if we impose the constraints too strongly, we have a hard Diophantine problem. It's coming back here, right? That's why I was emphasizing the connection with elliptic curves. The hard Diophantine problem is to find geometries that satisfy those constraints. We may just run out of all of our density of states, and so we can't actually perform the path integral. So we have to impose them weakly enough that there are some geometries that satisfy them. On the other hand, if we impose them too weakly, we won't get the right dynamics out of the theory, right? That we saw that we needed the constraints in order to get the area Regic action to have good classical equations of motion. So this is the twofold, the Charybdis and Scylla that we're navigating between. So what is an effective spin foam? I can define it now. It's a sum over these spin labels on our triangulation with a measure factor, amplitudes due to the triangles in the area Regic calculus action, amplitudes due to the simplices in that action, and the gluing constraint piece. And the idea of the spin foam is to try and go over all such triangulations, all such labels, I should say. So the way that, that an effective spin foam achieves this weak gluing, this weak constraint, is by choosing coherent states that are peaked on good dihedral angles, but don't strongly impose those dihedral angles, so that we still have enough density of states. So that's the idea of the theory. We make several numerical approximations in order to study it on a computer. So we consider symmetry-reduced triangulations. That is, we're going to consider configurations where a bunch of the areas are equal just to make it easier to compute the thing. We approximate the coherent inner products by real Gaussians. This is an even weaker implementation of the constraints where we just say, okay, we're going to take it to be Gaussian peaked around the good dihedral angle. And the wonderful thing is that we can show on a laptop in a matter of hours instead of weeks and days, we can show that there's a good semi-classical regime of the dynamics when we scale with both the area spectral gap, gamma, and the spin labels. This has become a huge community of people working on these things. I've included everybody that's working on both the effective spin foams and on the area metric geometries here, so I'm kind of blurring lines a little bit. But Bianca Dietrich's group and many of her students and postdocs have been working on a lot of these things. I'm going to just show you one numerical example. It's actually an old example. I figured that most of the people at the conference will be, most of the people that are working on these things will be presenting much more recent results, so I think I would just present the one that I was involved with. This was a symmetry-reduced triangulation that has an internal edge and hence has gravitational dynamics. This triangulation consists of 6 force implices, and it's a symmetry reduction. And here I'm describing that reduction carefully, but I'm running low on time, so I'm not going to go through it in detail. Here I'm giving even more details where you can see which areas are identified in the symmetry reduction. But the main point that I want to give you is that in a classical length Regic calculus, you can find the deficit angles around, say, these areas, this area as well, and you get these values in the length Regic calculus. And in our spin foam model, you get complex deficit angles. That's expected because we only impose the constraints weakly, so there should be some violation. But you can see that quite nicely, these are in excellent agreement up to the small violations that are coming from the weak imposition of the constraints. So this is beginning to make spin foams a very computable approach. The Lorentzian EPRL models are also becoming computable, but they have to use very computing intensive codes in order to do the full summation over the spin foam, and here you can do this on a laptop. It's really a much faster model. It's very approximate in the sense that we use these coherent states to impose the gluing, but the beauty of this approach and why I was putting so much emphasis on the gluing constraint is that, that every spin foam model should have some gluing constraint. So you could go to EPRL, and if you worked it out carefully, you could figure out what its gluing constraint is, and you could approach EPRL from the same perspective. It was this that we had in mind when we called these effective spin foams, but you could also think of these as a fundamental, excuse me, a fundamental model for quantum gravity. So just to summarize very briefly, you can think of an effective spin foam as being roughly made up of 3 pieces. There's a measure factor. I didn't talk about this at all, but the expectation is that that measure factor would come from thinking about coarse graining of your triangulation or careful treatment of diffeos in an approximate Regic calculus sense. The area Regic action is what we use to actually make the action of the theory, and then these gluing constraints, which is where I wanted to put the emphasis on this spin foam model, impose the good dynamics of the theory. Thank you very much.
Thank you, Hal, for this beautiful overview talk. Questions? I'll be running up.
Can you comment on the problem of corresponding loop space results to the results that those of us who do covariant quantum gravity perturbation theory calculations obtain?
So there's a couple of things that I can mention just very briefly. So you can compute in this spin foam approach, you can compute, for example, the graviton propagator. You're computing it at lowest order. Or another way of saying it is these spin labels, as you think of them as large, you're taking a sort of semi-classical limit of the theory, right? If you think of J over H bar, then the large J limit is a large action limit. And in that limit, the lowest order in the graviton propagator agrees with perturbative. In what background? I mean, this would be in a flat background. So that we're taking a 4-simplex model, and so we would be thinking of it as a flat background. I should be careful in how I say that because the background is sort of emerging as the semi-classical limit of that propagator. But there's much more to be done and connected between the perturbative theory and this loopy approach, right? Because the loopy approach doesn't want to work on a background. You want the background to emerge from the dynamics. And so as a non-perturbative approach, there's much to be done to further connect the coarse graining of that. The result I just told you is on the extremely simple triangulation. So you'd like to coarse grain that and see more thoroughly that you're working on a background of a standard perturbative sort. So this is very much an area where the understanding of the renormalization of the theory needs to come in to give us a stronger connection. That said, recent work that Bianca's done on the linearized theory in these area metric variables shows that in the linearized theory, you have a really good connection with the standard perturbative results on flat backgrounds, for example.
Thanks for this very nice overview. So something that struck me was the prominence of the Euclidean tetrahedron. So I'm wondering, isn't there a bit of tension between this exact Euclidean structure and the search for UV gravity? I mean, should we think of this tetrahedron as being something fundamental, or what is the connection?
Thank you very much for this question. As part of the International Society of Quantum Gravity, I just gave a course in the basics of quantum gravity, and I give many more details there, and I really go deeply into this question, but I had too many tasks to do today. And no, I do not think they're fundamental at all. So one place that I was trying to emphasize that was when I was saying that these should be thought of as fuzzy tetrahedra. We are fixing only 5 of the 6 classical parameters, right? And as such, the quantum state that you're talking about is spread out over that whole 6th parameter. So no, you should definitely not think of little tetrahedra at the bottom of space-time, right? This is like a coarse graining. I'm working with a finite number of degrees of freedom. Which ones? The dihedral angles between 2 faces and the areas of the faces and the volume maybe, right? Those are the ones that I described at various times in the talk. And those are, it's like, you know this beautiful picture of Baez and Buns of seeing the Einstein equations as I take a ball of test particles and I use the central particle to give me a proper time, and I measure how the volume of the ball changes in time. And that is the Einstein equations. So that's a beautiful picture. But they have an infinite number of particles to give that description, test particles, right? This is like I have 4. I don't have an infinite number. I'm describing a hugely truncated set of degrees of freedom, right? a tiny little subset of all of the gravitational degrees of freedom. And I'm only using this truncation because I can work with it mathematically and get a leverage from it. So we definitely need to understand what it means to refine this geometry.
But still, the relations between your variables are set, in a sense, exactly by the Euclidean tetrahedron. This is what you're using as a starting point. So one can argue or discuss whether these relations are indeed the simplest ones to work with. So I wonder whether this, is the strategy clear that one should be sticking to the variables of the Euclidean tetrahedron, even though you say we should be fuzzy?
I was very careful to say it's not just Euclidean, right? It's Euclidean and Lorentzian. And maybe another sort of piece of work which I referred to during the talk, but I can mention now in more detail, Laurent Friedel and Daniele Pranzetti and Mark Geiler and company have been looking at this kinematics of these surfaces in the continuum theory, the two surface. We call it the corner, right? Because you're imagining two Cauchy slices in space-time meeting at a corner. At that corner, you can study this two surface, and you can study the kinematics of that in the continuum theory. And beautifully, they obtain a fluid description of that. And the fluid description can be quantized. And the density of the fluid on the boundary surface is describing the area variables. So even at the level of the continuum theory, you're getting that same structure emerging. So do I think the tetrahedra have answers to everything quantum gravity? Absolutely not. Profoundly not. They are a coarse graining, right? It's just a coarse graining that you can get a handle on and that you can understand the basics of the theory from. But there's a lot of work that's happening now that's very exciting, that's connecting these pictures, right? That's not saying that they're totally remote from each other, that you can actually work with the Casimir of the diff S2, the diff of this corner region, and that Casimir is giving you the same sort of description.
Thank you very much, Hal. That was great answers, great questions. Let's thank him one more time.